ionic radius. Let us now mention about the ionic radius. Now we should not just say it is doing this and this. No, we have to reason. And if you reason correctly, you don't even have to put it in your head, because every time it comes, you just reason out and find the answer, you write it. So how does the ionic radii, what is the trend for ionic radii across this period? We are discussing from left to right. How does it change? So I have already drawn the ions for sodium and sulfur here. Sodium formed an ion by losing an electron. Magnesium, the same. Let us see them stepwise. Aluminium, the same. The three of them will form an ion by losing the electrons in the last energy level. First, let us discuss the three of them. That means this one is really demanding. Really demanding, but let us do it. Let us talk of sodium. Sodium was 281. It formed an ion, and the new configuration now becomes 28. Let me write for both magnesium and aluminium in the same way. Magnesium, aluminium. Good. The configuration for the ions is all the same, only that this is sodium N plus, this is magnesium 2 plus, this is aluminium Al 3 plus. From there, let me write the balancing. Okay, not the balancing. Let me not mention that one now. Let me write the number of protons, comparing them to the number of neutrons. So what I mean is, this one, sodium, has I'll be writing the ion here, ion, no, the electron, and then the ion. The best term was the atom. The atom and the ion. Sodium has 11 protons and 11 electrons. We already compared the sizes of atoms and ions of these metals. We did that for sodium, 281, 28. We said that the atom is bigger than the ion. The same to magnesium. And the same we hold for aluminium, because aluminium is atomic number 13. 283, its electronic configuration. The ion of aluminium is 28. The ion of aluminium is 28. The atom, that means this one has more energy levels. Everyone can see that this one has more energy levels, that translates to a bigger atomic size as compared to the ionic size. So let us not compare the ion and the atom. Let us compare. We want to see the trend in the atoms by itself. So what I'll do, I'll just write the ions alone, and say that the ion of sodium has 11 protons and 10 neutrons. Good. The ion of sodium, it has 11 protons and 10 neutrons. Sorry, it has 11 protons and 10 electrons. We are comparing positive charges and negative charges. 11 protons, the number of protons does not change since it is the atomic number, and 10 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 neutrons. That of magnesium has, we're still talking of the ion. Yes, the ion, we are using this. It has, the atomic number is the number of protons. It has 12 protons and 10 neutrons. Yes, 10, because it lost 2 electrons. Oh, I'm continually saying neutrons. And 10 electrons. And then you have aluminium. It has 13 protons and 10 electrons. Hey, now we are somewhere. We are now comparing the number of protons and the number of electrons. 11 protons, 10 electrons. And the same case to number 2 and our aluminium number 3. Now, what we want to say is we want to check on the trend in the ionic size. We just pick the first 3. Let us talk of the trend in the ionic radius. And here we'll be just be asking ourselves which one has more nuclear charge. Which one has more nuclear charge? We have this one. It is 10 electrons being pulled by 11 protons. This is in the nuclear. 11 protons are pulling 10 electrons. Let us revisit that. This one, 10 protons are pulling 10 electrons. You can guess that is stronger than this. 12 protons for magnesium are pulling 10 electrons. This one is stronger. This one is smaller because we have a high number of protons pulling the same number of electrons. This is 11 pulling 10. This is 12 pulling 10. This is 13 pulling 10. Which one is smaller? You know, the more they are pulled, the closer they will be to the nucleus. The more they are pulled, the closer they will be to the nucleus. This one is the smallest. That will be the smallest. Yes, the smallest. Because it is 13 protons pulling 10 neutrons. 13 protons pulling 10 electrons. Okay, we have seen the trend from here to here. I didn't want to mix the trends. Let us go now and compare chlorine and not argon, because argon does not react. It does not form ions. Let us compare. I think I'm done with this. Let us compare chlorine, sulfur, and chlorine. Sulfur and chlorine. They are ions. Sulfur configuration 286. Chlorine configuration 287. How do they form ions? They form ions by sulfur gains 2 electrons and it becomes sulfide ions 288. These ones becomes chloride ions. Chloride ions gains 1 electrons, become 288. Good. The ions have the same configuration as it can be seen on the board. 288, 288, gains 2, gains 1. Let us compare the number of protons and neutrons in these ions now. For the sulfide ion, good. For the sulfide ion, it has 16 protons because the atomic number is the same as the number of protons. It has 16 protons and it has, look at this. Let us add to the number of electrons. This is 8 plus 8, 16 plus 2. It has 18 electrons. Let us look at chloride ions. Chloride ions, atomic number 17, 17 protons. And the same number of electrons here, 8 plus 8 plus 2. That must be 16, 18 protons. And now we talk of the same thing, the nuclear charge. The nuclear charge. Now, talking of the nuclear charge, now we are considering the number of protons and neutrons. Which one is pulling more? Which one is pulling more? We have, and also remember, as we discuss it in that way, we have to remember that it is the same number of energy levels. The same number of energy levels. Like this one, there are 2 energy levels in all of them. So we have to consider that. This one is the same number of energy levels. When I say the number of energy levels, I mean the number of protons takes the lead, irrespective of the number of electrons. The number of protons will be leading. It can be 16 and 18. In fact, this one seems to be weak. But what about this? 17 protons and 18. Oh, sorry that I wrote P. 18 electrons. 17 protons and 18 electrons. This one will be smaller because the nuclear charge will be higher. A higher nuclear charge simply means the electrons are pulled more to the nucleus, and since they are pulled more to the nucleus, it means that they are closer. And once they are closer, the size of that ion or atom becomes very small. This one is smaller. And which is it? It is that of chlorine. So it is good that you have done all this. We have compared this and this. And what have we seen? On this part of metals, the smallest one was aluminium. On this part of non-metals, it still holds. The smallest one is chlorine. And therefore, it is very right to say that it is for the whole of this group. As you move from left to right, let us discuss the ionic radius. The ionic radius decreases just as the atomic radius. So it decreases from left to right, and you don't have to reason all this because now in your head you know that it is because of the increase in the number of protons that holds the electrons firmly and hence closer, making the ion small. Done with that. Ionization energy. We won't be mentioning much about this, not because we don't want to, or not because no, I mean in the same group there was the ionization energy. We can refer to it maybe first ionization energy. This one got 1 and 2. Aluminium got up to 3. So, and let's maybe just talk of the first ionization energy across the maybe these metals alone, because the other part we said that they use electron affinity. Let us mention it. It was and what you want to do is you want to compare sodium, magnesium, and aluminium. That is it. This one got a configuration of 281. This one got 282. Then got 283. Good. And what we are saying, we want to compare their first ionization energy. And what is that? It is the minimum amount of energy required to remove an electron from the outermost energy level of an atom in its gaseous state. So when we say first, it means for sodium, it is the energy required to remove this one electron. For magnesium, not these two, but one of them. And I mean the very first one to be removed. The same case to aluminium. The ionization energy required to remove the first electron from that. And let us do this. Which one requires the highest amount of energy? When you talk of energy, you simply means the same. The nuclear charge. Again, yes, again. Let us do it. The nuclear charge. And from what we have just seen from 2 minutes ago, sodium 11 protons, 11 electrons. Magnesium 12 protons, 12 electrons. Aluminium 13 protons, 13 electrons. The first ionization energy to remove only one electron. Now we just determining which one is easier, and the one which is easier, it will mean that it has, what am I saying? We want to determine ionization energy, which one requires the highest or the smallest. How much energy do they require, so that at least you can see the trend from sodium to magnesium. We said over here they use electron affinity. This one because they don't lose, rather they gain. Okay, let us do this. Sodium, it has first, you can use the knowledge about which one is smaller. I think that is the easiest. Aluminium is the smallest. And why is it the smallest? Because the electrons of aluminium are pulled more closer to the nucleus. They are pulled more because it has a bigger nuclear charge due to a high amount of protons. The high amount of protons pulling the electrons so close, and therefore aluminium atom is smaller than that of magnesium and sodium. It is smaller. Now, since it is smaller and it is pulling them closer, and you want to take one electron away from it, you want to take one electron away from aluminium, it is pulling them closer. What do you expect? It won't be that easy. It won't be that easy. But for sodium, it can be relatively easy because for its atom, it's big. So you can take away from it easily. Magnesium, a bit easily also. But for aluminium, which are pulled closer, they are pulled closer, and therefore, to take an electron from it, it will be work done. I mean, we can now conclude. Ionization energy between the sodium, magnesium, and aluminium. The first ionization energy. This one is needed more because they are pulled more. Therefore, if we go to that direction from left to right, ionization, no, let's not include this. Just the three elements, sodium, magnesium, and aluminium. Ionization energy from this part to this part. We don't want to make a mistake that we had made earlier here. So this one is small. Oh, the smallest atom, but it requires the highest ionization energy. Highest ionization energy. So let us compare them. This one does not require that much. So what is the trend? Is it decreasing or increasing? When we talk of the highest there, of course, it is increasing. So we say ionization energy is increasing from left to right for these metals. Yes, because we said it won't be used that, but the trend is it is increasing from left to right. Good. And the reason I why it is increasing is because those elements that are further away, as we go from left to right, there is an increase in the number of protons. And therefore, to lose an electron becomes hard. Okay, for them to lose an electron, we require more energy to lose an electron due to a higher nuclear charge or a higher nuclear attraction. When I keep quiet, I'm checking if I said the right thing. And of course it is. Yes, it is increasing from left to right because of the increase in nuclear charge. That leads to the electrons being held so firmly. That means losing that electron will require a lot of energy. I want to give the values for the ionization energy. I hope they have given and see if what we are saying is right. So I'll give the values for sodium, magnesium, and aluminium. Ionization energy. Trends across a period, just a single minute. Ionization energy. They have not provided bond type, structure, atomic, electron arrangement. They have not provided, but I'm also happy that we now know it. Yes, we even have some knowledge which is not there, but that is it. And I believe that is examinable by the way. Even if it is not in the book, it is very examinable. But it's good that we discussed and we have seen what ionization energy is and what fast ionization energy is, and we have discussed how the trend is. So done with this ionization energy, let's go to melting and boiling points. Melting and boiling points of this, the same idea. So we won't dwell so much on that. We have sodium, we have magnesium, we have aluminium. Let them come first. We said that this one has a small atom. Small atom. Then earlier we had said for metallic bonds, we have two factors that affect the strength of metallic bonds. One of the factors, size of the atom. The other factor, number of delocalized electrons. This one, sodium is 281 with only one delocalized electron. Magnesium 282, 2 delocalized electrons. Aluminium 283, 3 delocalized electrons. So the higher the number of delocalized electrons, Am I sure? Right? The higher the number of delocalized electrons, the stronger the metallic bond. So automatically, this one has a higher number of delocalized electrons. Aluminium is more stronger. Also, we have seen it has a small atom. The smaller the number, the smaller the size of the atom, the stronger the metallic bond. And with that, we can say that the melting point and the boiling point of these three metals, first, since they are metals, it is high, and then the trend is it is increasing from left to right. Increasing, yes, increasing, because we have an increase in the strength of the metallic bond due to an increase in the number of localized electrons, and also an increase in a decrease in the size of the atom. Then let us do this. We have phosphorus, sulfur, chlorine, and argon. First, these are molecular substances. They are molecular substances. We are checking on their melting points and their boiling points. Molecular substances have covalent bonds. They have covalent bonds. That is one thing. And on top of having covalent bonds, we have covalent bonds between atoms forming molecules. Between one atom and the other one, we have a covalent bond. And from there, between, after an atom bonds in an atom, they form a molecule. And now between a molecule and another molecule, we have van der Waals forces. And these van der Waals forces, I believe you've heard that word before. Okay, van der Waals forces. Van der Waals forces. These van der Waals forces are weak forces. They are weak forces. And for them to break, they only require a little amount of energy, and they are broken. And therefore, these elements have relatively low melting and boiling points. That is one reason. They have weak van der Waals forces that